All right, so now we're going to introduce this notion of a limit. And what I have here is I've drawn what potentially could have been our good friend y equals x squared. And what I'm doing here is, what if? No, it turns out this doesn't happen. But what if there actually were separate individual points if you magnify sufficiently? So this is a what if scenario. If that were to occur, it would look something within the limits of my badly drawn picture, something like this: discrete individual points that from a faraway scale would make it look like there actually is a smooth curve going through there. All right? So what I have here is this point. This is A, comma. I've just picked the number on the y-axis. I'm just going to call it. I picked a number out of the blue, or letter out of the blue sky. I'm going to call it L for no reason whatsoever. I've just chosen the letter capital L to call this value. Again, I just picked a letter out of the blue sky for no reason at all. I'm going to call it L. So this is the point A, comma L. So what we want to do, we want to verify that this never happens. We want to verify this is not what's happening. All right? This is not what's happening. Well, in order to describe what we don't want to happen, maybe we should describe what actually is happening here. If we describe what it means if this does happen, then it'll be a little bit easier for us to reverse it and say, okay, we don't want that. This is what we want. So what I'm going to do is first say, what is this? If this actually occurs, how do you describe that mathematically? And then how do you turn that around so you guarantee that doesn't occur? That is our task for this next little discussion here. All right? So, another sort of disclaimer. I understand that in the realm of quantum physics, if you understand what that means, there actually is a shortest distance in the known universe. We are talking about mathematical ideas, and so we are not constrained by physical reality. These are ideas, ideal constructs that are mental constructs. Again, the philosophically it's called in the Platonic world, but we're just saying we're assuming mathematical purity rather than physics, irregularity. So if you want to study physics, that's wonderful. But we're talking about pure, the way things are supposed to be, mathematics. All right. So what do we mean by saying this does occur? I have a phrase, I have a way of writing it here. It says this: that there exists, if this is happening. This is if it does happen. This is what we don't want to occur, but I'm going to describe what if it did. If this were happening, it would mean this: that there exists a small scale. A small enough scale. We have zoomed in on our scale small enough. What do we mean by small enough scale? What I mean is this: the interval of the number line we're talking about. Remember, we started way out from here, and we started with a large interval here, and we made our little box. We started with a great big interval. But what we have now, we've taken that and magnified it. We're now onto an extremely small interval. And so, rather than say a small scale, what I'm going to say is a small interval. That makes it a little more mathematical already. There is a small interval around L. Now, what does that mean? Look, this point is separated from the next one up and the next one down by a certain distance. So what I'm going to say is there is an interval here and here. I have an interval around L. Now my picture is terrible. That is supposed to be the same interval above as below. So let's see if I can fix that just a little bit. So within the limits of my badly drawn picture, this distance and this distance is the same. There's an interval centered at L. All right, so here's the top of it. Come on, come on. And here's the bottom of it. All right? That interval. There is a small interval around L, and what's happening? And we're saying this. As X gets close enough. Now look, if I choose an X that's very far away from A, we know the function value is not going to be in that interval. If I choose a function value very far away from A, I know this function value is not going to be in the interval. But in order for this gap to happen, what it means is this. No matter how close we get, even if I choose as close as possible to A, the function value never gets inside this interval. That's what we mean by saying they're separated. That there is a gap between individual points. That there is an interval around L so that no matter how close, as X gets closer, or I'll say close enough to A, if I choose my X value way out here, yeah, I know what's happening. What I'm saying is, yes, this is outside of the interval. Yeah, that's because it's so far away. This one's outside the interval. Yeah, that's because it's so far away. No matter how close I choose my X value, if there's a gap, no matter how close I choose my X value, this function value is never, ever going to get inside that interval. That's what we mean by saying there's a gap. That's what we mean by saying they're separated. If this gets close enough to A, the function value f of x, I see my function value f of x, stays outside my little red interval. So kind of let that set for a bit. See if that nestles into your mind a little bit. This is what we don't want to have happen. This is what I'm claiming never occurs. If it were to occur, this is what we're talking about. That there's a small interval around L, and you get close enough to X, no matter how close you get to X, the function values never get in there. Now, it is true, you might need, maybe the points are relatively closer together than what I've drawn here. And here's A, and here's L. But as long as they're separated, you could choose a small enough interval around L, see my small enough interval, so that if I magnify this, I get this picture again. Because the only difference between here and here is the scale of magnification. And so on a small enough scale, if they're separated on a small enough scale, there's going to be an empty interval. All right? This is what we don't want to have happen. What does it mean if this doesn't occur? What does it mean if this does not occur? That means no matter how small I get, it means that the function values do get inside of here. Well, what does that mean? Well, if this function value is inside of here, look, there still can't be a gap, because then I could choose an even smaller interval, and then I'm in the same thing. So what this says is, no matter how small you choose, no matter, here, I'll write it down here. This is what it means if this is happening. This is what it means if this circumstance is not happening. This is what we want to have. If this is not happening, it means this. For any, I'll make this any, for any interval around L, no matter how small we choose, no matter how small the interval we choose around L. For any, however small interval you choose around L, what has to happen? Well, let's draw a picture of the smooth curve and see what we have. What we want to have, what we claim is happening is this. That if I choose an interval around L, and again, imagine this, I'm writing this large so you can see it on the screen. Imagine this is extremely small. That, now not all the function value, if I choose an x that's very far away, well naturally they're going to be outside. I'm not worried about what happens very far away from A. What I'm worried about is what happens as x gets very, very close to A. And in this case, if x gets close enough, if my x value is close enough, what happens to my function value? Do you see it? My function value actually does fall inside that interval. And no matter how small you make that interval, you can get sufficiently close. You can get close enough so that that x value gets inside there. Suppose I choose a very, very small interval, so small that it's hard for you guys to see it at that scale. We understand that you still could choose an x close enough, and now it's really hard to see what's happening here, but that function value would still be inside that interval. For any interval around L, you can get close enough to A so that f of x is in the interval around just enough space around L. Now pretend you can actually read my handwriting. If this is not happening, if the dotted lines is not happening, so this is what we want to have happening here, right? So we want to have this occurring. So this is what we want. If for any interval around L, no matter how small we choose, for any small tiny interval around L, you can get close enough to A so that f of x is inside that interval. Let me draw that picture better here. That would mean this is the picture. Here's A, here's L, there's my curve. All right, I'll draw this relatively large, but understand in reality, the interval I'm drawing is going to be so tiny that you probably couldn't even see it even if you were here physically in the room. But I would have a very small interval around L. What we want to say is you can get close enough to A that this function value is inside. Not just that, every one of these function values is inside of that little interval. If that happens, that guarantees we do not have the separate individual discrete points. That guarantees we do have. The only way this can occur is if you have a nice smooth curve. So that's the rough. You might have to watch this a couple times and listen to me say it slower again. The big thing for now is to get the basic idea of what it is we're trying to have happen. And now what I'm going to do is talk about the specific details of how do we transition from this very, very poorly stated notion into something that's a little bit more rigidly mathematics. So that's what we're going to be on about next.